All right, so now we move on to lesson 5, rearranging formulas. So if we're looking at rearranging formulas, well, this differentiates from our previous lessons because now instead of dealing with just an x, a y, or whatever variable we may be dealing with, mq, whatever it could be, now we have at least two variables that are going on here. And our goal is to still isolate whatever variable we're looking at, but now we have two variables. So let's consider a couple examples here where two variables being involved in any given equation is important. Well, consider the following. What if I gave you a equals L times width? Well, we would recognize that the a that's isolated here represents the area, and that L and W are length times width. This is actually describing the area of any given square or rectangle. We then look at E equals mc squared. Well, the E stands for energy, and the person that made this equation famous is Albert Einstein. So it's talking about energy here. Now, when you go into physics, you'll be dealing with a lot of this in Science 10, where physics has a bunch of different scenarios where you may be looking at potential energy and kinetic energy. So this is fairly common here. Now, if we look at example C here, this one a little more tricky because we haven't reached trig in grade 10 yet. At this point, we would just have to identify that A stands for the angle or some given angle here, and where trig is some, or where the trig identity tan is being involved here, and there's tan theta is equal to some angle here. When you go into 10C, you'll deal a lot more with trig identities, sine, cos, and tan, but for now, just know that this is some application. And then finally, well, a squared plus b squared plus c squared, we know this is actually just our Pythag identity, or the Pythag theorem. So we can call this Pythag theorem. And more specifically, what does C represent, or the isolated variable here? It's actually our hypotenuse, which I'll just short form as hypot. So we know C squared, or the isolated variable, is our longest side. A squared plus B squared are the other two lengths of this given triangle. If I really wanted to, I could draw this off to the side here. We have a right angled triangle where C is our longest side, and then we can randomly assign A and B to the other two lengths. Okay, so we now know a couple different applications for multiple variables going on within any given equation, and what it means to isolate them is we could be looking for area, energy, angles, or even something like a side length. Now, when isolating for any given variable, we must do the opposite operation. I can't stress that enough. It's always the opposite operation that helps us when isolating a variable. So consider the following examples here. We have example 2. Isolate x in the following equation. So I'll highlight x just to indicate that that's the variable we're going to be solving for here. If we look at A, well, to isolate for x in this case, what we need to do, or what we could do, one option would be to add the 2 to both sides. We know this because it's the opposite operation of subtracting 2, and we should always see that we have a plus minus, or whatever the case is. So now we have y plus 2 is equal to x. And just like I said before, a congruent or an equivalent form in this case would be to write x on the left-hand side and have y plus 2 on the right. That is also a-okay, and we actually know that this would be more common to any multiple choice or any like diploma or final exam style questions. So just be more aware that our isolated variable typically appears on the left when it comes to answers. All right, now we go over to B. We have y equals x divided by some number, which in this case is 2. If we know it's being divided, then the opposite operation is to say we need to multiply it to both sides. So I'll multiply 2 to both sides. This becomes 2y is equal to, and if I have a number being multiplied and divided on the same side, it actually cancels both of those, and I'm just left with x. Yet again, we know that x can be isolated on its own on the left-hand side and whatever else was on the right. These are congruent forms or equivalent forms. All right, going down to C, we have y equals x squared. Well, something squared, the opposite operation is to square root both sides. So I'll square root both sides. This becomes square root y is equal to x. And yet again, I can write x on the left is equal to the square root of y. I can exchange them across the equal sign as long as I keep all the terms constant here and realize that these are both congruent or equivalent forms. Lastly, D, we could do this two different ways here. So just to demonstrate how things can be a little bit variable in equations, what if I start by subtracting 2 across? So I'm going to write the original, y is equal to 2 minus x. If I subtract 2 across and subtract 2 across, this is going to give me y minus 2 is equal to negative x. We know the coefficient on anything. This was from polynomials, this is from exponents. We knew if the coefficient wasn't written, we could write it in as 1. Technically, we have negative 1. And then what I can do is either multiply or divide by this negative 1 in order to flip the sign here. What I'm going to do is, because I always want to think about it in terms of it's negative 1 times x, the opposite operation would always be to divide by the negative 1 and divide by the negative 1. Now, when we multiplied by a negative 1, it flipped the signs of everything. Division is no different. If I divide by negative 1, this becomes negative y plus 2. It flips the signs of both the other terms, and this is equal to a positive x because we had a negative over a negative, which becomes positive. Now, the other way to solve this would be to say, what if instead I wanted to make the x positive right away and deal with the other numbers here? So I could rewrite my original, y is equal to 2 minus x. What if instead I added the x instead of dealt with the 2? I get y plus x is equal to 2. And now we know that if y is being added to x, we must subtract it from both sides or use the opposite operation. X is equal to 2 minus y. Now you may be asking, what is the difference? Because clearly these don't look identical. Besides x being on the left and x being on the right, and that being one of the differences, we also see that the order of 2 and negative y is different. With these, they're not different. We have a positive 2, a negative y, and a negative y. As long as the terms hold their consistent values, it doesn't matter if we put the positive value first or the negative value first. These would actually get you full credit regardless of which way you did it, because they symbolize a congruent statement or something that has equivalent value. So this is totally fine. As long as it's the right terms, it doesn't really matter their order. The only time order would matter is, let's say we were in polynomials and they said write it in terms of descending order. Well, we would know that a y should come before the 2 just based on descending order. But that's neither here nor there. I wouldn't focus too much on that, just as long as you can get to the appropriate simplified solution regardless of whether it's written as the negative or positive value first. Okay, now isolating a variable, we know that when we isolate a variable, we want to solve using the order of operations or BEDMAS, but when we're isolating for a variable, oftentimes we're going to be going in the reverse orders, and this is just a natural way of solving these. So let's consider the example below here. Suppose I give you the example y is equal to x minus 6 over 2 plus 3, and I want to solve for the x value here. Well, what I'm going to do is I'm going to try and isolate everything that's attached to that x, and this is going to revolve around things that are in the reverse order of operations. Here's what we mean by that. Suppose I start with the original equation. Well, my first order of operation is to actually subtract or add. We know by standard BEDMAS that would be our final step, is to add or subtract, but in terms of solving for some x value that has a bunch of operations to it, we know in this case what we're going to do is we're going to subtract away this 3 or deal with addition and subtraction first. I subtract away the 3, I get y minus 3 is equal to x minus 6 over 2. The opposite of division or dividing by 2 is to multiply by 2. Technically what they're doing here is they're saying if I multiply both sides by 2, what do I get? Well, I get the below a line here. 2 times y minus 3. We know our 2's cancel when we multiply and divide, leaving us with the x minus 6. Now, finally, to get x isolated, I need to do the opposite of subtract 6, which is to add 6 to both sides. Therefore, I get a solution of x equals 2 times y minus 3 plus 6. Let's look at a couple examples of our own here. Suppose we were given the following statement, y equals 3x minus 2, and we're asked to isolate for x in these equations here. So what I always do is when they give us a left side, right side, I'm going to start by writing out the original equation, 3x minus 2. Okay, we have our original. Now we want to isolate for x, so everything we do has to revolve around isolating for x. If there's anything attached to x like a negative 2 here, we know we have to do the opposite operation of this right away and add 2 to both sides. My next line is y plus 2 is equal to 3x. Now, I have something attached to x through multiplication. The opposite of multiplication is to divide by that value. Therefore, we have y plus 2 all over 3 is equal to x. There's our isolated term. We have x alone. All right, let's go over to example B. Like I said before, we're going to write the original. Y is equal to x over 2 plus 6. If I see anything attached to that x term or the term with x, I need to deal with that right away. The opposite of addition is to subtract 6. I get y minus 6 is equal to x over 2. Something is being divided from x. That means the opposite operation is to multiply by that value. So in my next line, I have 2 times y minus 6 is equal to, I know the 2's go away because it was multiplication and division happening in one step. Those are opposite operations. This is equal to x. The last thing I would do here is just expand the brackets or expand the 2 into the brackets. This becomes 2y minus 2 times negative 6, which is 12, is equal to x. There we go. Okay, let's go over to our next page here. So now we have a bunch more examples here. They're increasingly getting more complicated. Remember what I said to do. We're going to write the original. 4 times 2x plus 1 minus 4. All right. If there's anything attached to the thing with the x, in this case it is the minus 4, we need to do the opposite operation here. We're going to do, actually, what we could do here is, this might actually be a better way to solve this. What if I wrote out y is equal to, and I expand the brackets here. So I apply the 4 into the brackets. This becomes 4 times 2x, which is 8x. 4 times 1, which is plus 4, minus 4. We actually see that we can combine like terms here. We have a plus 4 and a minus 4. Those are going to eliminate, and we get y is equal to 8x. Now, with the thing that is attached to the x, in this case 8, it's being multiplied, so we need to divide both sides by that value. Therefore, we get y over 8 is equal to x. Okay, let's go over to example D. Let's try and solve this one using, potentially even an LCM would be really ideal here. We see this thing happening in the denominator, and we know from our first 3 lessons that a possible way to solve this would be to use an LCM. Y is equal to 3x plus 1 all over 2 minus 2. So what I'm going to do is I'm actually going to deal with that negative 2 outside here first of all. So I can say that this would be added across because it's subtracted currently. This becomes y plus 2 is equal to 3x plus 1 all over 2. Now, we know the LCM, or whatever's in the denominator here, is just actually equal to 2, so I'm going to multiply both sides by 2. Multiply both sides by 2. So this becomes 2y plus 2 is equal to 3x plus 1. Now, why was the 2 not multiplied into the numerator? Because it was canceled by the term 2 in the denominator here. And now, what we're going to have to do is we're going to actually have to expand the right-hand side and then use simplification from here. So what we can do is we can go 2y plus 4 is equal to 3x plus 3 when we expand the right-hand side. Now, I'm going to subtract away the 3 from the right-hand side, subtract it away from the left-hand side. I'm going to have to continue my proof off to the side here. This is going to become 2y, our plus 1 in this case is equal to 3x. Lastly, we have a term being added or being multiplied to x, so I need to divide by that term. So I get 2y plus 1 over 3 is equal to x, because we know things being multiplied and divided on the same side will cancel. Therefore, there is my x term here. All right, let's go to our next example. We have y equals 5 over 2, x plus 7 plus 5. What I'm going to do is I'm actually going to use the LCM right away. So I know I said I was going to do that in the last problem, but here's how we can demonstrate it on this problem. If we have our original y is equal to 5 over 2, x plus 7 plus 5. Well, we know our LCM is actually equal to whatever's in the denominator, the only term, which is 2. If I multiply both sides by 2 here, multiply both sides by 2, and remember it's everything on the left and everything on the right, this becomes 2y is equal to, well, the 2 over 2 reduces down to just 1. And then we have the 2 times the 5 on the outside term, or 2 times the 5 here. So we get 5 times x plus 7 and 2 times 5, which is equal to 10. If I subtract away the 10 from both sides, this becomes minus 10 minus 10. So now I have 2y minus 10 is equal to, I'm going to expand the brackets on the right-hand side, 5x plus 5 times 7, which is 35. I'll subtract away 35 from both sides, giving me 2y minus 45 is equal to 5x. I have one last step. It's to divide by the term being multiplied to x. And therefore, my final solution is 2y minus 45 all over 5 is equal to x. There's my final solution. Okay. Now, let's consider the example here. We have a is equal to c plus d over x, and we want to isolate for x. Well, there's 4 variables going on, but we want to isolate for x. Here's how we can do it. We're going to write the original a is equal to c plus d over x. We know that x is an LCM. So what I'm going to do is I'm going to multiply all sides by x in order to get that x out of the denominator. My left side becomes a times x is equal to x times c is cx, and then d over x times x, those x's cancel, and I'm just left with plus d. Here's where things get a little unique compared to some of the previous problems. If we have multiple terms with the same variable we want to isolate for, what we have to do is we have to move everything with that variable onto one side and everything else onto the other. I'm going to subtract away cx from both sides, leaving me with ax minus cx is equal to d. Well, what is my GCF, or the common term on the left-hand side here? They both share an x. From polynomials, we knew to factor out an x or take some x and place it out front. A minus c is equal to d. If anything's being multiplied to x, what do we typically do? We divide by that value. So I'm going to divide both sides by a minus c, therefore giving me a solution of x is equal to d over a minus c, because we have a common factor on the left of a minus c. Okay, let's see a comparable example below. I see 2 things with the variable that I need to isolate for. What does that mean I need to do? I need to take all those things and place them on one side. I have 2x plus 1 equals xy. This is our original. What if I subtract the 2x from both sides? This is going to give me 1 is equal to xy minus 2x. I would realize that a GCF here from the right is x. They both share an x, so I get 1 is equal to x. If I take an x off both these terms, I'm left with y minus 2 on the interior. And finally, x times this y minus 2, I need to take away the y minus 2 from both sides through division. Y minus 2. Therefore, 1 over y minus 2 is equal to x. All right, let's see another way we could have solved this, because we subtracted the 2x to the other side and solved it that way and got this solution. But instead, what if I subtracted the 1 across and then moved the xy to the left? Here's what I mean by that. What if we start with 2x plus 1 is equal to xy? I subtract the 1 from both sides instead of the 2x. That leaves me with 2x is equal to xy minus 1. I'm now going to subtract the xy, leaving me with 2x minus xy is equal to negative 1. I'm going to remove the GCF of x, rewriting this as x with leftover 2 minus y, and this is equal to negative 1. We know anything attached through multiplication to that x must be eliminated through division. And finally, I would get x, and I'm going to do it off to the side here, x is equal to negative 1 over 2 minus y. Well, if we compare our two solutions here, we did it one way, and we did it another way, and here's where our two solutions. X equals 1 over y minus 2, x equals 2 minus y, or x equals negative 1 over 2 minus y. The biggest difference we see right away here is that we have a positive y and a negative y. We have a negative 2 and a positive 2. What's the difference here? We can actually force these to look alike. If you got these as your solution, they would both be totally correct, no marks deducted. However, if we want to force these to be the same, I want you to realize that a negative 1 can be transitive across two different parts of this equation. We can actually put the negative 1 in the numerator or the denominator. And here's what it would look like to force the terms to be alike. If I have a negative 1, remember, if I'm either multiplying by a negative 1 or dividing by a negative 1, it can cancel, or it can reverse the signs of the given equation. Here's what I mean. I can have 1 over, I could shift that negative 1 to the denominator as a multiple of whatever's in the denominator, therefore giving me x equals 1 over negative 1 times 2 is negative 2. Negative 1 times y is a positive y, so I could write it as y minus 2. Now, you would realize that these two equations actually shared the exact same form to the t. Our final answers are the exact same. So what you can do is, if you realize you have a negative 1 involved in the equation, or a negative value involved in the equation, it can actually directly reverse both of the variables, or both of the things involved. In this case, a y and a 2, both of the signs will flip. All right, let's work on the you try section here. You try. Remember, we always want to start by writing the original. Y is equal to 9 over 2 x minus 3. I could add the 3 across right away, or I could multiply everything by the LCM that's equal to 2. So if I multiply everything by 2, both the left and the right, this becomes 2y is equal to 2 times 9 over 2x. The 2's will cancel here, giving me just 9x. And negative 3 times 2 is negative 6. Now, I'm going to add 6 to both sides, which is the opposite operation here. This is going to give me 2y plus 6 is equal to 9x. I'm going to divide both sides by the 9 being multiplied. Therefore, I get 2y plus 6 all over 9 is equal to x. Now, I could reduce this if I wanted to separate these in terms of separate fractions. However, I'm going to leave this as one fraction together and leave this as my solution. However, if I really wanted to, in blue, what I could do is separate this in terms of 2y over 9 plus 6 over 9 is equal to x. And I could further reduce this as 2y over 9 plus 6 over 9 reduces to 2/3 is equal to x. So that's if we really wanted to further reduce it or further simplify. However, this answer we have here is totally fine. All right, now we go into our final example here. I have the original of y is equal to 2 times x minus 4 plus 3. If I see this type of scenario, I may as well expand the right-hand side and see if I can collect like terms. Y is equal to 2x minus 2 times negative 4, which is 8, plus 3. When I collect the like terms, I get 2x. Negative 8 plus 3 is negative 5. I'm going to add the 5 across here, add the 5 across using opposite operations. I get y plus 5 is equal to 2x. Finally, I have something being multiplied to the x or the variable I'm looking for. I'm going to divide by that value. Divide by that value. Therefore, my final solution is y plus 5 all over 2 is equal to the x. Because I know if I have something multiplied and I divide it, it cancels, and therefore that is my x value here. All right. Now it's time for the check your understanding. This is very important to check your understanding here because there's a couple of these that will involve you having the same variable twice. How do you deal with that? You need to find some GCF. There's a couple more examples that will for sure need practice. If you need me, come see me in a tutorial. I'll be able to answer your questions on these.